So up until now, when we were talking about acid-base reactions, we were comparing anions or conjugate bases where the negative charge was on different atoms. We were comparing O minus versus N minus or F minus versus Br minus. But what if the negative charge is located on the same atom, as we observe in this reaction above? So basically the question we're asking, will this anion called phenoxide anion deprotonate cyclohexanol to produce phenol and this alkoxide ion. So in other words, we're asking which of these two anions is more stable. Is it phenoxide or the regular alkoxide? Now notice that in both cases the negative charge is on the oxygen. So you probably guessed it by now. The phenoxide ion is more stable, and it's more stable due to resonance, right? So then the equilibrium will favor this side. If you're having difficulty with resonance, make sure to review this topic. In the meantime, I will show you how many resonance forms the phenoxide ion can have. So if we go over here, so let's draw this one first, and I will draw it big so we can better see how the arrows are pushed and the electrons are pushed around the rings. Okay, so we have something like that. I will number the carbons. These are 1, 2, 3, 4, 5, and 6. So I can take this negative charge and convert it to a pi bond. But if I do that, then I have to convert another pi bond to a negative charge. Otherwise, my carbon 1 will have 5 bonds. So then it goes like this. So now we've got an additional resonance form. And the resonance form looks like this. So now carbon 1 is here. Carbon 2 is the one that has a negative charge now. And carbon 3 and 4 still have a pi bond between them. And so do carbons 5 and 6. I can then push these electrons over here to make a pi bond between carbons 2 and 3 and place these electrons on carbon 4. That will give me an additional resonance form. So now, over here things did not change on the top. So now we have carbon 1, we have carbon 2. There is a pi bond between 2 and 3. There is a negative charge on carbon 4, and 5 and 6 have a pi bond. So now I can take these electrons and push them over here to make a pi bond between carbons 4 and 5, and these electrons will then rest on carbon number 6. All right, so now we have the following resonance form. Carbon 1, carbon 2, there is still a pi bond here between 2 and 3. There is now a pi bond between carbons 4 and 5, and a negative charge on carbon 6. And then yet another resonance form can be drawn, where then these electrons form a pi bond between carbons 1 and 6, and these electrons come back to oxygen. So now we've got this situation where this is O minus, and we have carbons 1 and 2. Carbon 2 and 3 have a pi bond. Carbon 4 and 5 have a pi bond. And carbon 6 and 1 have a pi bond. So you have a total of 5 resonance forms for this anion. Resonance forms. If we look at the other anion, the alkoxide of cyclohexanol, no resonance forms are possible. No resonance. If you don't understand why there are no resonance forms possible, make sure to review this topic. So due to resonance, the phenoxide ion is more stable than regular alkoxide. All right, so now let's look at this series of carboxylic acids. Here we have acetic acid, the stuff in your vinegar, and it has a pK of 4.80. But look what happens as we start replacing hydrogen with fluorine. if we just place one fluorine on the neighboring carbon, the pK drops to 2.59. If I have two fluorines, the pK is 1.34. And if I replace all three hydrogens with fluorines on the neighboring carbon, the pK drops to 0. This is called trifluoroacetic acid, and it's obviously stronger acid than acetic acid. In fact, it's about 10,000 times stronger. What is going on here? Let's look at the respective conjugate bases, as we always do. Now, what we are seeing here is that the negative charge is in all three cases located on oxygen on the same atom. And in all three cases, this negative charge is stabilized by resonance. However, the secret lies in the neighbor. If we look at acetic acid, this carbon that is bearing this is called carboxylic group is connected to CH3. CH3 is an electron donating group. Think of this carbon as helping out its neighbors with electrons. It's feeding electrons into this carbon. Because of that, then there exists a repulsion between this carbon, which are going to circle, and the negative charge on the oxygen. This destabilizes the bond, making this anion unstable or less stable. Now, if we look at the other extreme, now, after we replaced all the hydrogens with fluorines, now this is CF3, and this in fact is electron withdrawing group. So now, it's because fluorine is pulling electron density away from this carbon has to ask for help of its neighbor, and it says, you know what, carbon, I'm going to get some of your electrons. The electrons are flowing that way. Because of that, this carbon in the circle, now it has a partially positive charge. Because of that, this negative charge in oxygen is attracted to this carbon, making this a stable bond. And as a result, this anion is more stable than the one of the acetic acid. This phenomenon is known as inductive effect. The formal definition of inductive effect is permanent polarization of sigma bonds within the molecule due to the presence of electron withdrawing groups. You can think of it as if you have an anion and you have an electron withdrawing neighbor next door, that will stabilize this anion. That would increase its stability. All right, so now let's look at this series of compounds. Over here we have ethane, which has a pK of about 50. Now we have ethene. Now we go from single bond to a double bond, and the pK drops to 43. And here we have acetylene. Now we went from double bond to triple bond, and the pK drops even further to 25. So what is going on here? Why is it that alkyne is a stronger acid than alkene and even stronger acid than alkane? Let's look at the respective conjugate bases. So over here we have negative charge on carbon in all cases. And no resonance stabilization is possible here. No inductive effect is observed. So the only difference is in hybridization. In the alkane, the carbon is sp3 hybridized. In alkene, is sp2 hybridized. And in alkyne, it's sp hybridized. Now, if I were to draw these hybridized orbitals, then if I were to draw sp3 hybridized orbital, it would look like this, right? The s is this little dot, and the P character is this giant oval. To me, this looks like a bunny with very large ears, right? Now, if I move to sp2 hybridized atom, now bunny's head gets bigger and is more proportional to the size of the ears. And as I move to sp hybridized atom, now I have a lot more S character. Now, it doesn't even look like a bunny. Now it transformed into a piglet. Large head and very small ears. The more S character the hybridized orbital has, the more spherical it is. So that means that the more spherical it is, and the electron is within this sphere in case of sp hybridized orbital, the stronger the nucleus attracts that electron. The closer that electron is to the nucleus. Think about it. Here, the electron is in the sphere. In the sp3 hybridized orbital, the electron is probably in somewhere in this oval, right? Somewhere here. So it's a lot further from the nucleus. It's attracted with a smaller force. So the more S character you have, the more acidic your compound would be, the more stable is the respective conjugate base.